Bayes nets. Okay, what's a Bayes net again?
It's one of those things with circles and lines.
Yeah, it's got circle. You got it. But what is it? It's a circle line thingy.
It's a representation of the chances of things happening based on probabilities and other factors. And if certain things are true and certain things are false, you can calculate the probability of things.
The probability of things happening. That's pretty good. Let me do a textual substitution for thing and say the probability of a particular arrangement of the world. Yeah.
That's what I meant.
Yeah. What's the three-word definition for that thing you just said?
Probability distribution.
Joint probability distribution. Because it's joint because you got a lot of variables all joined together, holding hands in a big happy circle. So it's the probability that all those variables have those particular values. That's what you would look up in the joint probability distribution. And a Bayes net represents the entire joint all together. Wow, that's a lot of stuff. And it's compact, so it's a compact way of representing a joint probability distribution. Who cares? Why do we care about Bayes nets? Oh, I'm glad you care. Why do you care? Why does anyone care? Who cares about Bayes nets? What the hell? Why we have so few seconds on this earth? Like, I don't know about you, but I'm getting older. So this whole thing about why do I care is like super important to me these days. So like I don't do anything that I don't actually feel is super important. I feel like teaching people AI, super important. Here I am. I'm not going to live this day a second time, as far as I know.
Develop predictive models.
Predictive models? Yeah, that's cool. So if you want to predict something like, but also just understanding the world. Like, whoa, my phone rings, it's John calling. How freaked out should I be? Bayes net can tell you that. You know?
90% freaked out.
You should freak out with probability 0.9. Yeah. Other interpretations of why we should care about Bayes nets?
Does it just make calculating a long sequence of probabilities really easy?
Well, I think it's really hard, but if you think it's easy, that's awesome. Good for you. It's long sequences of probabilities. We're not really going to talk about sequences until we get down here, so you're jumping the gun a little bit. It allows you to reason with things that you don't know everything about. And let me tell you, the more I live on this earth, the more I realize we don't know everything about most things. So if there's any uncertainty, if you can't fully quantify all the preconditions of some logical assertion, you're off in probability land all of a sudden. It's not like there's a burglary, the alarm is going to go off. Nuh-uh. If there's a burglary, there's some probability the alarm's going to go off. And if the alarm goes off, there's some probability that John is going to call. It's all probabilistic here. It's all like mostly, kind of, usually sort of stuff. And that's the way real messy life is. And so if you want to deal with that, if you're an agent in the world, you got to reason with probabilities. A Bayes net is the best way anyone's come up with to reason with probabilities. Maybe next year someone will come up with something better, but for the last 20 years it's been this. So how to reason with how to make probabilistic inferences. You know, John and Mary are both calling me, telling me my alarm's going off. What's the probability I should rush home and there's been a burglary? Whether you should rush home or not, for some probability there's been a burglary, I guess, is a very subjective thing that isn't represented here. But you could make a decision if you had a certain threshold, like if there's more than a 1/3 chance there's been a burglary, you're going to go home, then.
So if you were to use the same model but just take the probabilities and make everything either like a 1 or a 0, would that turn it into propositional logic?
Basically. Yep. The probabilities turn out to be helpful in practice. But one thing that they did a study at Stanford where they came up with a lot of early applications of Bayes nets to medicine. They got a nice hospital there right next to a really nice computer science department. They took their Bayes net system. That's what they developed. The first expert system that was ever better than humans was developed at Stanford Medical School. It was diagnosed bacterial infections of the blood. It's called Mycin, and it was like way better than any human. So at that point, it's like it's immoral not to study AI, right? Like you're going to heal people better if you use the computer than if you don't, which I think is pretty radically cool. And you think about trying to lower healthcare costs. All these radiologists looking at X-rays all day. Oh yeah, they're going to be right on their toes the 100th X-ray they see that day. Much rather have a computer vision system look at my X-rays, I'll tell you. Anyway.
Depends. Because I mean, if it's a learning system,
it's already been trained.
What was it trained on?
People just like me. Yeah, there's a certain modeling assumption that, like, you know, the network holds for whatever your reality is. But I think it's amazing how similar people are. I mean, if you think about how much is similar between, like, the C. elegans little worm thing that, like, lives in dirt and us, it's like, whoa, we share 80% of our genome. It's like, it's a little dirt thing. It's like, doesn't even have a backbone. Okay, where were we? Why do we care about Bayes nets? Because they're awesome. They let us do probabilistic reasoning. Okay, so we're going to do another example of reasoning with Bayes nets. How the hell do we reason with a Bayes net? Anybody remember? There's a whole bunch of big formula things, but whenever you get in a situation like that, of course, you got to be able to reason it through. The reason that Bayes nets are awesome is because they specify what's independent, or what's dependent, and thereby what's independent. Something's independent if the probability of this variable, the probability distribution over this variable, given all these other variables, is independent of most of them. It doesn't depend on it. It only depends on the ones that are the parents. And so a joint probability from a Bayes net is, woo, let's multiply all these little teeny conditionals together. Just the parents. So that's super nice. So this is trivial. You all know how to do this, I'm sure. Yeah?
When you say independence, you're talking about like the same thing when you're talking about like independence of two random variables.
Exactly. Yep. The let's see if I can say this. It's just not true, yeah. You can't correctly specify its probabilities without talking about the probabilities of these things. Whereas these guys are independent of each other. Having a burglar, whether or not there's a burglary has no effect on whether there's an earthquake.
I was just going to ask, is that the naive assumption that naive Bayes makes?
Yeah, totally. Pa-ching! It's all coming together. Yeah, so that's the same sort of independence thing. Yep, exactly. So a Bayes, did everyone remember the graphical model for naive Bayes? Graphical model for naive Bayes. Ching, 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 ching. Your variables, not connected by anything. That's the naive Bayes graphical model. This was the mixture Gaussians. Like there's a variable saying what cluster am I in, and there's a variable saying what are my values. You don't get to see this. We have to infer it using EM. This is an MDP where this is a square because it's not really a random variable, but whatever the state we end up in, the variable, like if we treat if we treat S prime as a random variable, its value, the probability of getting a particular S prime depends on the value of the previous state we got. Like let's say I was in state 23. Well, that'll affect my probability of ending up in state 7. And it's also affected by what action I took. So these two things are influential in determining what S prime is going to be. And thank God for it. This is free will right here, that arrow. The actions you take can influence your destiny. I guess actually free will is whether we're taking those actions or whether the actions are deterministically selected by the mechanism of the universe. So maybe free will is a little more complicated than that arrow. Maybe there's really supposed to be an arrow coming in here. I mean, is the free will you're taking of the action, or is it the way the action came about being selected? If you were running the planning algorithm, then it's free will. If someone else is running the planning algorithm, but who programmed the planning algorithm? Maybe you're just running the planning algorithm, but it's still deterministic. Maybe it's all the programmer's fault. Oh, this is getting a little crazy. All right, so anyway, that's the naive Bayes model. Yeah. Okay. And that specifies independence, which is good. And this is the fundamental query for probabilistic reasoning. If there's some variable we're interested in, we know the variables of some, we know the values of some of the variables, and then there's other stuff that we don't know the value of. The nuisance variables. And for the third time, to compute the distribution of x given E, we decided that you could just sum out all the nuisance variables and compute the joint probability, compute the joint summing over all the different configurations of the nuisance variables with the evidence variables fixed at the values that they have.